Welcome aboard, where aviation concepts become simple. From instruments to aerodynamics, we make exam prep clear and cockpit learning faster. This is StudyKwik Aviation.
Welcome to StudyKwik. Today we begin learning about the direct reading magnetic compass. It's one of the simplest yet most essential flight instruments. We'll cover principle, properties, errors, and how pilots use it in practice. The compass uses the Earth's magnetic field to show heading. Specifically, it responds to the horizontal component of magnetic force. This helps pilots orient their aircraft relative to magnetic north. The aircraft's heading is based on this magnetic datum. A direct reading compass lets the pilot see heading directly. It does this with a pivoted magnet assembly attached to a compass card. One common version is the vertical card compass, also called the E-type. This type is widely used in light aircraft for simplicity. Its design allows direct heading readout against a lubber line. In larger aircraft, compass deviation must remain within limits. Typically, maximum allowable deviation is about 10 degrees on any heading. This ensures accuracy during navigation and cross-checking. The E-type compass has a circular card attached to magnet bars. This card floats in a liquid-filled bowl to reduce oscillations. A lubber line fixed to the glass marks the aircraft's heading. For accurate operation, compasses need three main properties. These are horizontality, sensitivity, and periodicity. Let's look at each in detail, starting with horizontality. Horizontality ensures the magnet system stays level with Earth's field, but at high latitudes, magnetic dip tilts the field downward. This creates a challenge for compass design. To solve dip issues, the assembly uses pendular suspension. Its weight shifts the center of gravity below the pivot. This keeps the card closer to horizontal alignment. Pendular suspension reduces dip but creates new issues. Turning and acceleration errors appear because of shifted weight. We'll explore these errors later in detail. Next is compass sensitivity, the ability to point to north accurately. This depends on both Earth's field strength and magnet design. Stronger, shorter magnets increase sensitivity and reduce lag. A jeweled pivot reduces friction at the suspension point. Lower friction means smoother, more responsive card movement. This further improves compass sensitivity. Now, let's consider periodicity, the time taken to settle. If displaced, the card oscillates before stabilizing on heading. Good design reduces oscillation duration for quick readings. Liquid inside the compass bowl improves stability. It supports the magnet assembly and reduces oscillations, but it also creates issues like expansion and swirl. Swirl happens when liquid drags the card during turns. This can cause temporary heading errors. It is especially noticeable in sharp maneuvers. Straight-line acceleration can also cause compass error. This happens when the pivot and center of gravity misalign. The card swings incorrectly due to inertia forces. For example, accelerating west at 270 degrees in the northern hemisphere, the compass needle may swing right, giving a false heading. This is a classic acceleration error. Deceleration causes the opposite effect. The compass swings toward the magnetic equator. This misreading is temporary, but critical for pilots to understand. At the magnetic equator, dip is zero. This means acceleration errors are absent. On north-south headings, errors also vanish. Turning errors are another major challenge. These happen due to magnetic dip during turns. They are largest on north-south headings. Errors are minimal on east-west headings, but liquid swirl can still introduce small inaccuracies. Understanding these helps pilots anticipate compass behavior. Example, turning left from 045 degrees to 315 degrees in the northern hemisphere. Magnetic dip causes the red magnet end to hang below horizontal. The pivot point being closer to red end creates an anti-clockwise couple. This forces the magnet to swing anti-clockwise. Because of compass card orientation, this looks like overreading. Pilots must correct mentally for the difference. In a right-hand turn from 315 degrees to 045 degrees, the opposite occurs. The magnet swings clockwise relative to the aircraft. This causes the compass to underread the actual heading. When the aircraft turns 90 degrees, the compass may show less. For example, a 90-degree turn could register only 70 degrees. Thus, the pilot must stop turning before reaching the desired heading. This correction is known as undershoot and overshoot. Pilots anticipate compass lag by adjusting their turn. This is especially important during instrument flying. Errors also depend on rate of turn. At rate 1 turn, error may be about 20 degrees. Rate 2 turns produce larger errors up to 30 degrees. In the southern hemisphere, turning errors reverse direction. This is due to opposite dip orientation, so pilots there must apply corrections accordingly. Terms like sluggish and lively describe compass motion. A sluggish compass lags behind the actual heading. A lively compass swings ahead of the turn. At the equator, dip vanishes, but swirl remains. Swirl alone can cause up to 5 degrees lag. This must still be considered in precise navigation. Liquid expansion is another challenge inside the compass bowl. When temperature rises, liquid volume increases. To prevent damage, an expansion chamber is included. This expansion chamber is usually a diaphragm or capsule. It absorbs liquid expansion caused by heating. Without it, pressure could crack the glass face. Let's examine them separately for better clarity. Permanent errors remain even in steady flight. They are mainly caused by nearby magnetic fields. Aircraft wiring, engines, and metals often create them. Deviation is the common permanent error. It's the angular difference between compass north and magnetic north. This is due to aircraft-induced magnetic interference. Deviation is corrected using small compensating magnets. They are placed in the compass mounting. Adjustment is done during compass swinging on the ground. Swinging the compass means checking its accuracy. Aircraft is aligned to known magnetic headings. Corrections are applied until errors fall within tolerance. A deviation card is displayed near the compass. It lists residual errors for each cardinal heading. Pilots use this card to apply corrections in flight. Transient errors occur only in certain conditions. They appear during acceleration, deceleration, and turning. Once motion stabilizes, the errors disappear. One important transient error is the northerly turning error. It happens when turning through north or south headings. Compass lag or lead causes underread or overread. Rule of thumb, UNOS. Undershoot north, overshoot south. This is valid in the northern hemisphere. In the southern hemisphere, the rule reverses. Here, compass errors are opposite due to dip direction. Thus, overshoot north, undershoot south. Another transient error is acceleration error. It occurs on east-west headings during speed changes. Compass swings due to inertia and dip effects. Rule of thumb, ANDS. Accelerate north, decelerate south. Again, valid only in the northern hemisphere. Example: flying west at 270 degrees and accelerating. Compass swings falsely toward north. When decelerating, it swings toward south. These errors vanish near the equator. That's because dip angle is 0 there, so no false swings due to acceleration. The greatest dip effects occur near the poles. Here, compass reliability decreases significantly. In some regions, compass use becomes impractical. That's why polar routes rely more on gyro instruments. Gyros are not influenced by magnetic dip. They provide stable heading information. Despite its errors, the magnetic compass is still vital. It serves as a basic, independent reference. Even with power or system failure, it functions. Pilots are trained to anticipate compass errors. They learn correction rules during instrument flying. This ensures safe navigation even without advanced aids. Let's now explore the installation requirements of compasses. They must be mounted away from strong magnetic fields. This reduces permanent deviation from aircraft parts. Compasses are usually mounted on the instrument panel. Sometimes they are fitted overhead on the windshield. Both positions minimize interference from avionics. Before every flight, compass checks are carried out. Pilots compare compass heading with known runway direction. This confirms accuracy within acceptable error. During flight, the compass should be cross-checked. Pilots compare it with a directional gyro or other sources. This keeps navigation precise and reliable. At night, the compass needs illumination. A small lamp lights up the compass card. This allows accurate heading reading in darkness. Vibrations can disturb compass performance. Aircraft structure and turbulence often cause oscillations. That's why damping liquid is essential. Modern compasses use clear, anti-reflective glass. This improves readability in bright sunlight. It also protects against dust and moisture. The compass bowl must remain bubble-free. Air bubbles affect card movement and accuracy. Inspection ensures the bowl is completely filled. Maintenance includes periodic compass swinging. Also, checking liquid level and expansion system. Any leakage requires replacement or repair. In summary, the direct reading compass is simple yet complex. It directly shows magnetic heading, but with predictable errors. Understanding these errors is key to safe flying. To improve accuracy, aircraft use gyro-stabilized compasses. These are called directional gyros, DGs. They eliminate dip and turning errors of magnetic compasses. The DG is powered by suction or electricity. A spinning gyro maintains a fixed reference in space. This stabilizes the compass card against erratic movement. However, a DG drifts over time. This is caused by gyro precession. Therefore, pilots must realign it to the magnetic compass periodically. DG is useful in instrument flying conditions. It allows smooth, accurate turns without compass lag. Pilots rely heavily on it for heading control. More advanced systems use remote indicating compasses. These combine flux valves with gyros. They transmit heading electrically to cockpit displays. A flux valve senses the Earth's magnetic field. It reduces interference from aircraft structure. Signals are sent to indicators inside the cockpit. The most common system is the Directional Gyro Indicator, HSI. It shows heading, course, and navigation guidance. This reduces pilot workload during navigation. An HSI integrates a compass with VOR-ILS systems. This helps pilots track courses precisely. It is standard in modern cockpits. Remote indicating compasses also drive autopilot systems. Heading information is fed electronically. Autopilot then maintains the selected direction automatically. ACE systems require careful calibration. Errors may still occur from flux distortion. Periodic checks ensure accuracy in all phases of flight. Modern aircraft use attitude and heading reference systems, AHRS. These are electronic sensor packages. They provide accurate attitude and heading data. AHRS uses accelerometers, gyros, and magnetometers. Data is processed digitally for high accuracy. They feed flight displays and navigation systems. AHRS are lightweight compared to mechanical gyros. They require less maintenance. They also integrate with GPS for error correction. Some aircraft have inertial reference systems, IRS. These are highly advanced navigation tools. They track position and heading without external signals. IRS uses ring laser gyros or fiber optic gyros. They detect angular changes with extreme accuracy. This provides stable heading even in polar regions. Inertial systems are independent of magnetic fields. Thus, no compass errors like dip or deviation. This makes them reliable in all environments. However, IRS can drift slowly over time. Therefore, it is often cross-checked with GPS. This ensures continuous precision in long-haul flights. With GPS integration, Heading accuracy is extremely high. Errors can be corrected automatically. This is called hybrid navigation. But still, the magnetic compass remains on board. It acts as the ultimate backup instrument. Even advanced systems cannot fully replace it. Thus, pilots are trained in both old and new systems. They learn basic compass correction rules and also modern digital instrument interpretation. Compass heading plus variation gives true heading. This calculation is basic but vital. It links magnetic instruments with geographic direction. In cockpit training, pilots memorize formulas. True plus minus variation equals magnetic. Magnetic plus minus deviation equals compass. This relationship helps cross-check headings. Errors can be identified quickly. Thus, navigation remains accurate. In summary, heading systems evolved greatly, from basic magnetic compasses to AHRS and GPS. Yet, fundamentals remain essential for pilots. Now, let's review everything step by step. We'll reinforce key points about compass principles and highlight practical pilot techniques. A magnetic compass works on Earth's magnetic field. It aligns with magnetic north. Simple, yet highly useful. Errors include variation, deviation, dip, and oscillation. Pilots must learn how to correct them. Memory aids like UNOS and ANS are key. Variation depends on location on Earth. It changes with time as poles drift. Charts provide current values. Deviation comes from the aircraft itself. Nearby metals and wiring distort the field. Compass swinging reduces this effect. Dip is strongest near the poles. It causes turning and acceleration errors, minimal at the equator. Turning errors follow hemisphere rules. Northern, UNOS. Southern, reverse it. These apply during north-south turns. Acceleration errors apply on east-west headings. Northern, ANS. Southern, opposite rule. Pilots anticipate false swings. Oscillation is simple vibration. It comes from turbulence and movement. Damping fluid minimizes it. A direct reading compass is always installed. It requires no power supply. It is the ultimate standby. Remote indicating compasses use flux valves. They reduce aircraft magnetic interference. The heading is sent electrically to displays. HSI combines compass and navigation signals. It is central to instrument flying. Reduces pilot workload significantly. AHRS replaced older gyros in modern planes. They use solid-state sensors. Provide digital data with high accuracy. IRS gives complete navigation independence. No reliance on Earth's magnetism. Used in long-range aircraft. Still, IRS drifts slowly over time. GPS corrections remove this drift. This ensures precise long-distance navigation. During training, emphasis remains on basics. Students first learn magnetic compass, only then move to advanced instruments. This builds strong foundational understanding, prevents over-reliance on automation, improves pilot confidence in emergencies. During check rides, compass errors are tested. Examiners expect quick correction recall. This proves pilot readiness. For example, during a north turn, the pilot must undershoot the rollout heading. This avoids overshooting the target. Similarly, during acceleration on an east heading, the pilot must ignore the false north swing. Instead, trust the directional gyro. Such practical knowledge keeps flights safe. Errors become predictable, not dangerous. That's why the compass study is vital. Regulations require compass installation. Even with advanced avionics, it remains mandatory equipment. Maintenance teams check compasses regularly. They refill fluid if needed. They inspect for bubbles or cracks. Deviation card is kept updated. It must match latest compass swing. Pilots rely on its correction values. Compass checks also occur before takeoff. Runway heading is compared with compass. Discrepancy must be within limits. If compass is unreliable in flight, pilot shifts to gyro heading, but keeps monitoring both systems. In polar regions, compasses are nearly useless. Gyros and AHRS are primary here. This is standard in long polar routes. In equatorial regions, a compass is most accurate. Dip errors are negligible there. This is where it works best. Thus, environment matters greatly for compass reliability. Pilots must adapt techniques by latitude. Knowledge plus practice equals safe navigation. Let's wrap up with a full review. We'll connect theory with pilot practice. This ensures complete understanding. The compass is the oldest navigation instrument. It's still required by aviation rules. Its simplicity is its strength. Errors are predictable and correctable. Variation, deviation, dip, oscillation. Pilots must memorize them. Rules unos and ands are memory keys. They prevent mistakes during flight. Easy to recall, easy to apply. Rules unos and ands are memory keys. They prevent mistakes during flight. Easy to recall, easy to apply. Gyro compasses solve many problems, but they require power and alignment. Compass remains the backup. Remote indicating systems bring accuracy. They integrate with autopilots. This is the step toward automation. AHRS and AHRS are next generation. They are reliable and digital, used in modern glass cockpits. Even with automation, human skill is vital. Compass corrections keep pilots sharp. They form the foundation of navigation. Emergency training emphasizes compass use. Simulators replicate failures. Pilots must rely only on magnetic compasses. Thus, training balances tradition and technology. It ensures pilots are always ready, both in normal and emergency cases. Aircraft manufacturers still design compass mounts. They consider shielding from interference. Placement remains a critical factor. Compass fluid has special properties. It must resist freezing at altitude and avoid evaporation at heat. Any leakage is a serious fault. It can impair accuracy. Maintenance teams check it carefully. A glass dome must remain scratch-free. Clarity is essential for heading reading. Protective covers are often used. Compass swinging requires trained personnel. They use calibrated compasses on ground. Corrections are entered on deviation card. Pilots are taught to trust instruments, but also to question unusual behavior. Cross-checking is key to safety. This is why redundancy exists. Multiple instruments provide backup. Compass is one of them. Navigators in early aviation relied solely on compasses. They crossed oceans with basic tools. This history underlines its importance. Even today, general aviation uses it constantly. Small aircraft may lack advanced gyros. Compass remains their primary heading source. Thus, compass knowledge is universal, from student pilots to airline captains. Everyone depends on it. During long flights, pilots compare systems. Compass, DG, HSI, IRS, GPS. This builds a complete navigation picture. Discrepancies may signal equipment failure. Compass serves as a cross-check. This helps in troubleshooting. Compass also aligns gyros initially. It acts as the reference heading. This is part of cockpit setup. Before takeoff, alignment is verified. Pilots ensure systems agree with compass. This is a standard checklist item. In flight, compass checks are periodic, especially after turns or unusual maneuvers. This ensures drift is corrected. Thus, the compass is not outdated. It is integrated with modern systems and remains a legal requirement. From theory to practice, compass knowledge is vital. It links ancient navigation with modern aviation, a timeless tool for pilots. Every flight you take, remember this. Behind advanced displays lies a simple compass, still guiding aircraft safely across skies. That's why training never ignores it. It builds discipline, awareness, and skill, qualities every pilot must master. In conclusion, the compass is simple yet irreplaceable. It teaches fundamentals of direction and ensures safety in all flying conditions. If you found this helpful, like, share, and subscribe to StudyKwik for more aviation lessons.